Welcome everybody. Let's take a look at a little review for your upcoming exam. You should have already taken your Chapter 9, Section 2 quiz. Hope you did well on that. Drawing the I circle, starting at the top. I is equal to the square root of -1, because you can't take the square root of a negative number. Then, if you had I times I, you get I squared. Well, square root of -1 times square root of -1 is equal to -1. A radical times itself, you end up with what's under the radical. Multiplying by I again, we would get I cubed. So you would have -1 times I, which is -I. We've got I, we've got -I. Multiplying by I again, you would have I to the 4th, which would be I squared times I squared. So -1 times -1 would be +1. And then we loop back around here. So I at the top, -I at the bottom, +1 on the right, -1 on the left. Simplifying I to the 15th, we could just go in a circle, starting with I to the 1st, 2, 3, 4, 5, 6, 7, 8. Who do we appreciate? 9, 10, 11, 12, 13, 14, 15 is here. This is equal to -I. 16, 20, 24, 28, 32, 33, 34, 35. Ooh, got the same thing again. Doesn't always happen, but sometimes it does. There's only 4 choices after all. Square root of -4, well, we can't do the square root of -4 because it's imaginary, but we can do the square root of 4 and get 2. The negative gives you the I. Next up, square root of -12, no decimals. So the negative is going to give you an I, but we need to think about numbers that multiply to 12. And one of them needs to be a perfect square, like 4, 9, 16, 25, 36, and so on. 12 would be 4 times 3. One of those is a perfect square. The 4. Square root of 4 is 2. The negative gives us the I, and we don't know the square root of 3. Simplifying radicals, no decimals. Let's get into our new stuff for today. Chapter 9, Section 4, looking at periodic data, cycles and periods of periodic functions, finding the amplitude of periodic functions. So periodic data is something that's going to have repetition to it. If something is periodic, like the periodic table, for instance, there's a pattern, there's repetition. We have things that repeat over and over again. And from there, we're going to end up seeing how trig graphs relate to periodic data. We should be able to identify cycles, periods, find the amplitude of periodic functions. So what do these things have in common? Waves keep crashing, Dumbo keeps rocking back and forth, your heart keeps beating, the world keeps turning. Well, they're periodic. There's repetition to them. Periodic function is one that repeats a pattern of y values at regular intervals. So those y values happen over and over and over again within a certain x interval. Some examples, well, sound waves, light waves, radio waves, your cell phone signal, if it didn't repeat, you wouldn't get much of a signal. Tides repeat over and over again. Your heartbeat has a pattern, has a rhythm. Otherwise, you need to see a doctor. Length of a day. Well, same number of days every week, every week, every week. There are 12 months in a year. Location of a piston in an engine. So as you press the gas, your pistons move up and down to a fixed height over and over again. And if they aren't exactly where they need to be, you're going to have engine trouble. Riding on a Ferris wheel. You're going round and round and round. There's my type of Ferris wheel. Cupcake wheel. Yeah. Let's spin it around. Ooh, I get that one. Let's spin it around. Yes. Give me another cupcake. flow of electricity. If you go plug something in, there's already electricity waiting for you because it's constantly flowing in a wave. It's periodic. And trig functions are periodic also. Here are some examples. Sine, you'll notice the same height at regular intervals. Same with cosine. Same with tangent. Oh my, look at all those asymptotes there at regular intervals. This graph is not periodic because it doesn't repeat. It goes like this, and that's it. It goes up forever, goes down forever, but there's no repetition to it. Cycle in the period. We call a complete pattern a cycle. The horizontal length of one cycle is the period. So think of your x-axis. From where does it start to where does it repeat that point? That would be that cycle. If I can find a place where it starts and it then repeats, I could count it over. So often we count starting at 0, so we have to find where this point repeats again. It repeats 2 units over. Same, 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 same. So every cycle is 2 units wide, whether you're looking from here to here, here to here, here to here, or from top to top, top to top. We look at this graph. Often we start at 0, so we're down in the valley, we're halfway between, go up and over and down, and we're halfway between the valley, so it is 2 units wide. That would be the length of a cycle. This graph here, finding 0, 0's here, so the middle here to the middle here would give you a width of 2 pi. In real life problems, the x-axis is usually represented by time. Electricians often deal with different types of waves. Engineers, triangular waves, square waves. Well, let's see if I can find 0 and go it's over 2 units. Is that the entire thing? No, because that just gets you this part. What about the bottom part, right? So this point here, we're going halfway up the mountain. We're halfway up the mountain, 1, 2, 3, 4 units over. So a complete cycle would be up, down, and halfway back up. How about our square wave over here, which really isn't all that square looking, looks more rectangular to me, but I didn't name them. So we go up and over, down. This is not one cycle. We need to get the bottom half also. So from here to here, we're going halfway up to halfway up. That's where it repeats. It's also 4 units wide. Different types of periodic functions. If I were to find, for instance, this one, starting at 0, it goes up and over and down. Keep going because that's downhill until we go up and, oh, it is 6 units wide. I don't know, those two remind me of Batman for some reason. From here, where does it repeat? Goes up, comes down, goes back up. It is 2 pi units wide. Speaking of how high it goes up, the amplitude measures the variation in a function. So to find it, one way is to take half the difference between the maximum and the minimum values. Subtract the max and the min and cut it in half. You're finding an average of that height. So if we're looking at this here, your amplitude from the midline, the middle of our graph, the midline, half of our graph is above the midline, half is below. Our amplitude would be from the middle to the top, the middle to the bottom. Should be the same distance. Your amplitude, here's our midline. Half is above, half is below. However much that distance is, would be the amplitude. We're looking at our sine wave. Well, we find the middle, that's our midline, half above, half below, whatever that distance is. V would be our amplitude. Whale calls are pretty close to being periodic. For being natural, we'll give them a little bit of a break here, but they have a repetition to their whale songs. If this is the middle, we can see that the amplitude is almost 0.3, almost down to 0.3. This graph here, 3 times sine of x. The middle of the graph is here. It's 3 units above. It's 3 units below. That is the amplitude. The period would be 0 to 2 pi. It repeats one complete cycle from 0 to 2 pi. Amplitude. We can change the amplitude of different types of waves to increase how far out it moves from something. So if I were to increase the amplitude, we can see that the waves are deeper and deeper and deeper, and then these are going to bounce into each other. It makes for a neat effect. Got some serious motion going on there. So let's take a look at the first thing you and your group are going to try out. And you should only spend maybe about 5 or 10 minutes working on this. You'll fill in a table, and then you'll graph it, trying to figure out, if you can get a periodic function out of it. So if we were to look at the times listed here, 10 o'clock, 10:15, 10:30, 10:45, what I'm looking for you to do is how many minutes until the nearest hour? So if it's 10 o'clock, you're right on the hour. That would be 0 minutes. If it's 10:15, well, the nearest hour is still 10 o'clock, so you are 15 minutes away. At 10:30, well, you're a half hour here, or you're a half hour to the next one, so you're 30 minutes away. At 10:45, how many minutes to the nearest hour? Well, the nearest hour would be 11 o'clock. You're back down to 15 minutes. So as you fill in your table, you're going to see some periodic elements to it. Graph each of those, draw the curve, and I think you'll see a periodic function. Take about 5 or 10 minutes, work on that. Come on back when you're ready. Welcome back. Periodic functions, we said, are ones which repeat. There's some terminology that we need to make sure we understand. A cycle is a complete pattern. This graph here shows us one cycle. Usually we find a starting point. 0 is a great place on the x-axis to begin. So if I'm starting, I'm here at the top of this little wave. I come down, I come back up to the top. From here to here is a length of 2 pi. That makes one complete cycle. That's the part that if I could copy and paste it over and over again, I would get more of my graph. So if I took this piece and I copied and pasted, I have the exact same thing. If I copy and paste, I have the exact same thing. So it's the entire pattern. The period is how long that cycle is. So in this case, the period was 2 pi. But for this graph here, the period is equal to 8 pi. We start here at 0, we go up to the top of the hill, we hit 0 again, but we keep going to get to the bottom of the hill, back to halfway up. So this point at 0 matches this point at 8 pi. This is one cycle with a length of 8 pi. The period is 8 pi. Our amplitude, 2 above the midline, 2 below the midline. Amplitude is 2. We said you could take the maximum minus the minimum and divide by 2. 2 minus negative 2. 2 minus negative 2. 2 minus negative 2 divided by 2. Well, that'd be 4 divided by 2, which is 2. Sometimes it's easier just to count from the middle, go up. How much? How much did you go down? One of the things that you'll do is you will be highlighting one cycle, finding the period and the amplitude of the periodic function. So let me highlight one cycle. So I need to pick a starting point, like maybe 0. I'm going to start here, and I'm going to figure out where does it repeat that. So I'm going up the hill. I'm halfway up the hill. I reach the top of the hill, coming back down half the hill, back to up half the hill. So highlighting one cycle would be from here to here. If you don't have a highlighter, I do keep a few over there by the calculators. Find the period and the amplitude. Well, the period is the length of that cycle. So from 0 to 360, that would be the period. The amplitude. Find the middle of the graph. The midline is here. So how far above, how far below? 1 unit up, 1 unit down. That means your amplitude is 1 unit. Highlight one cycle. Find the period and amplitude of the periodic function. So we'll start with finding a beginning point. Well, here's the beginning point. 0 on the x is often a good, easy place to begin. What are we doing? We are at the bottom of the hill here. So going up, coming back down. Looks like I repeat right here. To highlight one cycle, we go here. If I copy and paste that, do I get the entire pattern? So up, down, up, down. Yes. I can continue. Up, down. I just need to make sure I get the correct width and the correct height each time. So how wide is that cycle? What's the period? It goes over to 5. 5 units. Amplitude, we need to find the middle of the graph. Our midline, if we could figure out the middle is right here. So, how high up, how far below the midline do we go? It goes 2 units up, 2 units down. So our amplitude would be 2 units. If we couldn't see that, we could always go maximum minus minimum divided by 2. That would give you your amplitude also. Pi, oh my, Pi's out on a date. 3.14, Pi says there's a lot more to me than you think, because Pi goes on forever and ever and ever. You never really get to know all there is about Pi. I gotta go. My mom won't use my full name on I'm in big trouble. 3.1415926535. Get in here right now. Anybody else have that where you know you're in trouble when your mom breaks out your full government name? Yep. Mr. Brown, get in here right now. Yes, Mom. You and your group, why don't we take about 15 minutes to work on periodic functions. Hit pause, come on back when you're done. Welcome back. What I'm going to do is take a look at a little website here, and it's going to animate the sine curve. I want you to watch the y values as the sine curve, the graph of sine, is created from the unit circle. we know our unit circle repeats values over and over and over again. So therefore, our graph of sine is going to repeat over and over and over again. Starting at 0, ready, set, here we go. 0, 90, 180, aka pi, 270, 3 pi over 2, back to 2 pi, which gets us here. And you might go, well, the x-axis isn't labeled in degrees or anything. Well, it is. It's labeled in radians. 0 degrees or 0 radians is here. 2 pi is here. Pi is how much? Oh yeah, it's 3.14. So then we get to 2 pi, we're back to 0. What's happening to create our curve? What we're doing is we're taking the height, oh, now we're in negative y territory. We're taking the height, the red line, which is your sine value, the height of your triangles. And that height translates over here between 0 and 1 for the top half where sine's positive, A, C, T, S, and negative, C and T, where sine is negative down here between 0 and negative 1. So to create your sine curve, we just need to know the height of our triangle. In other words, our sine values at certain angles. This just happens to be doing it in radians. Hey, question for you. When math majors graduate, do they get degrees or radians? Oh, some of you are going to have to think about that soon enough. Whatever the height of our triangle is, like if we were to do 0 degrees, there is no height, we're at 0. If we do 90 degrees, well, we're here, it's 1 unit tall. Think of the point up here. Remember, it is 0, 1. You have a height of 1 unit. So our height of 1 unit. At 180 or pi, 3.14, you're back to 0. That would be here. At 3 pi over 2, you're down at negative 1. Well, that would be here. And then back to 360 or 2 pi. 2 pi is 6.28. There you are. Now we would clearly want some other points in between, because otherwise I can just see your graph right now. Oh yeah, I'm talking to you. I can see it. You're going to go here to here to here. And that certainly is not sine. Sine is a curve. It is not straight lines. So, how do we graph sine? That's what we're going to take a look at. Graphing sine. We need certain values of our unit circle. We need 0 and 360. Well, that's 1, 0, 0 being the sine value. We need our 90, 1. We need our 180, 0. We need our 270, negative 1. We need our 360, back to here. So if I were to graph those, here's what I get. 0, 90 is 1. Well, how about I make this a half, and I'll make that 1. I'll make this negative 1 half, negative 1, just to spread it out a little bit. 90 is up at 1. 180 is 0. 270 is negative 1. 360 is back to 0. Now it would be helpful if we had some other answers in here. Like, 1, 2, 3, 1, 2, 3. Remember those? One, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I can count. Look at me. 1, 2, 3, 1, 2, 3. Right, 30 degrees. Sine is a half. Well, a half would be right here. 0, 30, 60, 90. 60 degrees. Sine would be radical 3 over 2. Go ahead and put that in your calculator. Square root of 3. Don't forget to close your parentheses. Divided by 2. What do you get? Oh yeah, I got 0.866 also. So 0.866 would be right about there. How about radical 2 divided by 2? Put in your calculator, don't close your parenthesis. 0.707, okay? So if this is 30 and this is 60, then 45 is halfway in between, 0.707. Now we come over here and we get the same exact answers. 120 will match the 60. It'll be 0.866. 120 will be here. $150 will be the half. And in between 120 and 150 is your 135. It's at 0.707. So we're getting part of our curve here. Now let's do the same thing for the other part. 210, it's a 30-degree reference angle, so it should match a half. But keep in mind, ACT, it's now negative 1/2. 240, that's a 60-degree reference angle. That would be negative 0.866. And halfway between 210 and 240 would be your 225 at 0.707. These points reflect and mirror now. If we go to 300 degrees, this is a 60-degree reference, but it's negative. So we should be 300, negative 0.866. The 45 is going to be at 0.707. And the 330 is matching a 30-degree reference angle. It's going to be at negative 1/2. Here's your graph of sine. Now, when you guys are doing it, we don't typically use all of those. The ones we use are the ones in red. We use 0, 1, 0, negative 1, 0. Just don't give me those straight lines. Give me the curve. When you guys are graphing, the only ones we need really 0, 90, 180, 270, back to 360. If you have those 5 points, you can draw your curve. You'll do it both in degrees and you'll figure it out in radians. Have a great Viking day, guys. I hope everything went well. Sorry I can't be here. Let me make sure we don't have any homework. No homework. Best day ever. Bye.